since we're starting to learn about some more complex organic compounds, we started with alkanes and alkenes and that, but now we've sort of learned that there's a whole other level of organic compounds that are involved in some really interesting reactions. And one of the reactions that we're going to do actually is called saponification, which is quite a fantastic word. But anyone tell me what that actually means? What is the definition of saponification? Just take a shot at it.
To clean?
Sorry?
To clean?
To clean, that's, well, you'd be able to clean after you do this reaction. Basically, it's the release. Well, there you go. Nice one, Cassandra. It's the release of fatty acids from a triglyceride. And we haven't done triglycerides yet. We will when we get to the chapter on lipids. But we have already learned about the chemical link that links these fatty acids to the triglyceride, and that is an ester reaction, an ester bond. And so we're going to break an ester bond of a fat, fat being a triglyceride, and I'll show you the basically what that looks like. And we're going to release those fatty acids from the triglyceride and go from having a fat to having a fatty acid. And then, as Cassandra so helpfully pointed out, when we add a salt, then we'll be able to actually turn it into soap. So what are we talking about here? Come on. There we go. Oops, let me go back. So soap production. Basically, soap was found by accident. And it's kind of gruesome, at least the way I was taught how it was discovered. Back when people were dumping bodies in the river, places like India, they would burn. They would have a funeral pyre, and then the ash would go into the water. And nearby, people would also be burning wood to cook and whatever else they needed to do. And they noticed that in the water, in certain places where they had these wood fires and the ash had gone into the river, that they got this sort of bubbly substance. And when they put their clothes in there, they'd come out clean. It turns out that what they had discovered is that the animal fat, wherever that would be in these bodies, had broken down and gone into the water and mixed with the ash. The ash has a lot of sodium hydroxide in it. And so the pH would be very, very high. They would break the bonds of the fats and then release these fatty acids. And the fatty acids then form micelles and bubbles and soap. So what we're dealing with here is what a triglyceride looks like. And so you can probably understand where the tri comes from. We have 3 long acids. And you say these 3 are different lengths, but they're all quite long. So we've got palmitic acid on the top, I think has 16 carbons. And then lauric acid in the middle, I think that has 12. And then myristic acid. Obviously, these aren't the scientific names, which is 14 carbons. So when you have these really, really long hydrophobic chains, as we've learned, they like to orient themselves with other long hydrophobic chains and interact with each other through London dispersion forces. And so they're not going to be very water soluble. On the other hand, they do have a hydrophilic end. The hydrophilic end is the acid part. So what we have are these 3 ester bonds with glycerol. And glycerol is just, you probably heard of that, I would think. Glycerol is a tri-alcohol. It has 3 alcohol groups, one there, and one there. And so it forms 3 esters with these 3 long carboxylic acids. And so we know we can break these bonds. We can break these bonds by either strong acid or strong base. We'll pop them off. And then when you do, you're left with the carboxylic acid. Actually, you won't have if you do it in base, you won't have the hydrogen there. You will have sodium from the sodium hydroxide. And you'll have the alcohol groups put back on the glycerol. So that reaction is called saponification, because we have these long fatty, that's specific for these long fatty acids. So it's called a triglyceride because we have 3 fatty acids, and the glyceride part comes from glycerol. And there's going to be lots and lots and lots of different triglycerides. The longer these chains are, the greater the London dispersion force. And so if you have really, really long chains like C24, even all the way up to C30, those interact so tightly that will actually be a solid at room temperature. And that's where you get solid soap. If we have shorter hydrophobic tails, like C12, C14, C16, like we have here, they'll be liquids at room temperature. That's where you get liquid soap from. So it depends on the length of the fatty acid chains. So here's the reaction. So this is a fat. A fat is just basically the fatty acids connected to glycerol. And they can be of a lot of different lengths. And they don't have to be saturated. What do I mean by a saturated fatty acid? What does that mean? What's a saturated hydrocarbon? We learned about saturated and unsaturated hydrocarbons.
It's
What did
solid
that
at
mean?
room temperature.
What was it?
Solid at room temperature because of the single bonds.
Oh, okay, you're onto something there. It doesn't really have anything to do with whether or not they're solid or liquid at room temperature. Well, they do a little bit, but what's the actual meaning of a saturated hydrocarbon and an unsaturated hydrocarbon? You're onto something when you talked about their bonds. The bonds are different.
The saturated ones have single bonds.
That's right. And what do the unsaturated ones have?
Double or more.
Yeah, they have at least one double bond. That's right. So a saturated fatty acid would just look like this. All single bonds. And then an unsaturated fatty acid would have at least one double bond, and then a polyunsaturated fatty acid would have multiple double bonds. And the more double bonds they have, the more kinked their shape is, because we know that these double bonds lock things into place. And so instead of having a long chain that can basically, flop around and then take whatever shape you want, these kinks are put in it, basically bend these fatty acids and make it so that it makes it more difficult to stack these chains on top of each other. And that's why the more polyunsaturated fats you have, and this comes back to the point you were making earlier, the more polyunsaturated fatty acids you have in a fat, the more likely it is to be liquid at room temperature, because it prevents London dispersion forces from really taking over. It lowers the amount of interactions because they have these kinked shapes that don't lie flat on top of each other. So in this instance, we have coconut oil, and each one of the fatty acids has 18 carbons, 16 methylene groups, the carbon that goes on the carboxylic acid, and then a methyl group at the end. So they're all C18. Then, so 1 mole of this plus 3 moles of sodium hydroxide and some heat will then break these bonds right there. Break those bonds right there, leaving you with the hydroxyl groups intact on the glycerol. And so you can see all that this is just 1, 2, 3. Propanol, but it's 1, 2, 3 propanol, or 1, 2, 3. It does 3 hydroxyl groups. So you would say like 1, 2, 3 hydroxypropane. We just call it glycerol, and it's really, really thick. It's a very viscous substance because it has so much hydrogen bonding going on that this is a really, really viscous substance. It's really, really hard to measure. Believe me, I've had to measure it in the lab all the time because it basically pours like molasses. It's so super, super thick from all that hydrogen bonding. So that will be one of the products, is glycerol. The other one is stearic acid, now become stear-8. Remember, 8 we put down as the conjugate base of the fatty acid. And since we're using sodium hydroxide, it's going to be a sodium salt. Why won't this form stearic acid again? How come we get sodium stearate as a product and not stearic acid? Because I thought the reaction, we were supposed to get an alcohol and an acid, right? But here we're getting an alcohol and a base. What's up with that? Why is that? Think about what one of the reactants is. Specifically, this one. What is it about the presence of sodium hydroxide that leads us to make the conjugate base of the fatty acid and not the fatty acid itself? How come we don't get this group on the end? That's missing, and we're left with a negative charge. Yeah, so Vera says it's because we have a high concentration of hydroxide ions. That's true, but I want to know why the high concentration of hydroxide ions leaves us with a conjugate base and not the acid. Why is that? Just think about acid-base reactions. What happens to acids in the presence of a strong base? What does a strong base do? We know that acids donate protons. What do strong bases do? Man, you guys are supposed to be the lively group. What's going on?
It becomes neutral, right?
What becomes neutral?
The pH. I mean,
No, actually the pH will be very high. In the presence of sodium hydroxide, the pH will be very high. And what happens to acids in the presence of sodium hydroxide? Even weak acids in particular, like acetic acid and a fatty acid. They both have the same group. They both have the carboxyl group, which is a weak acid. What happens to a weak acid like acetic acid or a fatty acid in the presence of hydroxide? Like, what happens to this hydrogen specifically? I got a weak acid. I got a strong base. What's going to happen to this hydrogen in the presence of a strong base? Is it going to stay connected to the acid?
Forms water with a base.
That's right, exactly. It dissociates. So if you have a weak acid, like a carboxylic acid, basically any acid with a carboxylic acid group, they're all weak. And the length of the carbon chain really doesn't have anything to do with how strong or weak the acid is. They're all pretty much the same. And so just like acetic acid, like we did with the titration, when we added strong base to that weak acid, it deprotonated it. It pulled that hydrogen off of it and made water. What we were left with was the conjugate base. We were left with acetate, and we get exactly the same thing here. But instead of acetate, we get stearate because it's a different molecule. The only difference being it has a much longer hydrophobic tail. Acetic acid only has a very, very short tail, just has methyl group there. But stearate has a really long tail, but they're both weak acids and they both would undergo the same thing. So we're not going to get the acid at the end because there's so much hydroxide around. We're only going to get base. And since we're going to get the conjugate base, it's going to have a negative charge, and it'll form an ionic interaction with sodium. And that'll be really important later, because one of the experiments you're going to do is you're going to compare what these soaps do in the presence of sodium versus the presence of divalent cations like calcium and magnesium. So we'll talk about that in a minute, because that will be the experiment, the second part of the experiment that you're going to be doing yourself. So usually, like, commercial soap making uses what's called a hot method. They do exactly the same reaction we're going to be doing, but instead of using 1 molar sodium hydroxide, they use 6 molar sodium hydroxide, and they raise the temperature. It's an endothermic reaction. So the more heat you add, the faster it goes. And so not something we want to be doing on our stovetops with very, very concentrated sodium hydroxide. That would be a bad idea. So that's a, fairly dangerous reaction. It's a fairly dangerous 6 molar sodium hydroxide is something you don't want to mess with. That will put a burn on you that will be quite severe. 1 molar sodium hydroxide is bad enough. So what we're going to do tonight is just start the process. That's the so-called cold process with more dilute sodium hydroxide. We're going to use vegetable oil. We've been provided with vegetable oil, although you can use whatever. If you have something else, you can use something else. So just plain, I'm assuming it's just plain vegetable oil. I don't know if it's peanut oil or probably just regular vegetable oil like Crisco or something. So what we're going to do is we're going to weigh out about 2 grams of it, and then we're going to add our sodium hydroxide, and then basically shake it a number of times to form an emulsion. What's an emulsion? So we're going to make it, when we shake this up, we're going to form an emulsion. What does that mean? Yeah, it's like a suspension. And a suspension just means that we're going to form really, really, really small droplets, because if you take water and oil, they don't mix, right? The oil should float on the top because it's less dense than water. But if you shake it, basically, if you break up the droplets of oil till they're super, super small, then basically they will stay suspended in the water for a little while until they sort of, you'll probably notice they start moving back together and forming larger droplets and larger droplets and larger droplets till eventually they separate completely. So tonight we're just going to add them together and then probably shake them like 2 or 3 times. Because what we want to do, we want the reaction to take place. And the reaction is only going to take place if the oil is in the presence of the sodium hydroxide. If it separates, then you've only got a layer of oil on top or exposed to the sodium hydroxide. The reaction will only take place in that small layer. So we won't make very much soap. So we want to get as good an emulsion as we possibly can with as small droplets as we possibly can. So we get access to the sodium hydroxide. And then we're just going to leave it for like 3 days. And then you guys are sort of on your own. So what you're going to do next is a process called salting out. Now, what that means is you're going to be adding really concentrated sodium chloride. Then because you want those, what we call head groups, or the polar groups, the carboxylic acid part. You want all of them to be in the presence, all of them to be bound to sodium. When they're all bound to sodium, then they form much better micelles. And I'll show you what I sort of drew you a really ugly picture of micelle before. I'll show you a much prettier picture. When you form better micelles, they better separate themselves from the water, because we want to filter out the water and then be left with our soap. So you'll be salting out. I'll be doing the same thing. I'm going to do the reaction as well. So you're going to salt out the soap and help it separate it from the water. And then after that, you're going to test the activity and properties of the soap. One, we're going to take the pH. And to take the pH, we have these little strips of pH paper. So you have these pH strips. So what you're going to do is just take a little bit of your solution and spot it on the pH paper, and then it will change color just like the pH indicator we used earlier. And then check the color. The more basic it is, or the stronger the hydroxide concentration, the darker it gets. So you get, basically when it gets over, like neutral will be like sort of like a green, olive green, and then it just gets darker and darker and darker the more basic it gets. And it should be fairly basic. We will want to, one of the other things you're going to be doing during the salting out process is washing the soap to get rid of as much sodium hydroxide as possible, because basically no one wants to wash their face with sodium hydroxide or their hands with sodium hydroxide, because then it turns your hands into soap, and that's no good. So you want to have a pH less than 9. Anything greater than 9 and you really start to get like irritation on your skin. So this is what a micelle looks like. And so you can see how important it is for the presence of sodium, because it allows nice separation between the inside and the outside. So without it, you've got all these sort of negative charges that will be repelling each other and not allowing a micelle to form, because all these head groups are negatively charged. And if you have a whole bunch of negative charges, they're going to repel each other, and this is not going to be able to form. If that's why, that makes sense. So when we add a lot of sodium, we make absolutely sure that all of these negative groups are neutralized. And so then they can come together quite closely and form a micelle. So we have all the polar groups on the outside. All the polar groups are on the outside of the micelle. All of the non-polar groups are on the inside. So if you have, one of the experiments you're going to do is actually putting like a drop of the vegetable oil in the presence of the soap and see what happens. And what should happen is that micelles should form around the oil, and then the oil droplets should just basically disappear inside the micelle. So this is basically how membranes were formed. In a what we call a double layer or bilayer membrane, we have polar on the inside, and then a non-polar, or sorry, polar on the outside, and then a non-polar group on the inside. And then inside of that is a second layer with more non-polar groups, and then polar groups on the inside. And that's how cells were formed originally, because on the inside, now we have a hydrophilic or water-loving interior. And that's where you can put all of your, proteins, DNA, and everything else is now separated from the outside world. And it's the formation of these micelles that's responsible for that. So it's the formation of these micelles that's responsible for separation of inside and outside. And that's how it also works as a cleaner, because basically it takes dirt, completely surrounds it with the micelle, and then removes it from wherever it is. So that's why soap is so effective at cleaning, and why there's a whole bunch of different soaps. There's cold water soaps, there's warm water soaps. They're all slightly different based on what the head groups are. Let me go back. Based on what the head groups are, you don't always have to have carboxylic acid. You can also have bases. These can be amines or amide groups. So you can have basic polar groups on the outside. And by varying the length of the chain in the inside, you can have a whole variety of different soaps with different chemical properties. But they all are based on sort of making these micelles. Okay, so what are we going to need? So we're going to have, hopefully everyone found the little box or the little bag that says saponification of fatty acids on it. It pretty much has everything in there that you need. It's got the vegetable oil, hydroxide. We've got these screw top vial, which is very important. And then, so basically all we're going to need tonight is the hydroxide, the oil, and the vial. And then later, you're going to be doing the testing, okay? We will need the scale, and that's a plastic pipette. That's pretty much it for this evening. The other stuff is for later. So we're going to use about 2 grams of vegetable oil. So we just put this directly on the balance, tare it, and then we just drop liquid in it with the, I think they even give you a transfer pipette in here to use until you get about 2 grams. Then we're going to measure 2 mils of the 1 molar sodium hydroxide. Be really careful with that stuff. Put it in the container. Really make sure that you tighten the cap. You don't want this to be loose and sodium hydroxide to be going everywhere. So make sure you tighten it down. And then we're just going to shake, 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 and then form an emulsion. And then we want to make sure that there's no distinct layers forming. If we shake it well enough, basically you make those droplets so small that they just stay in suspension. So we're going to let it sit for 5 to 10 minutes and then shake it again and make sure that there's no distinct layers. At that point, then find a place to put this until Saturday or Sunday, however long you want to take to finish the reaction. So after that, you should form a solid. I mean, eventually those are going to form 2 layers again because you've got oil and water. So now you should have fatty acids and water. And so the fatty acids should be forming micelles. So you should have I don't know how solid it's going to be because I haven't done this experiment myself. I don't know how solid it will be, but we're going to filter it, and then we're going to wash it. Oops. And then we're going to wash it with the saturated sodium chloride solution. So that is the salting out. So we want to make sure that all of the conjugate base is bound to sodium ions. Then we filter it, and then you actually do the experiments with it. So you take about a 0.5 gram put it in the 100 ml beaker with 50 mils of water, and then mix it up. Then we've got these 2 glass test tubes. Put 5 mils into each one. And then we're going to take the pH. And also do this with some liquid soap in your house. You probably have some liquid soap in your house. And if you don't, you can just use some solid soap as well. But we want to compare what you've made with a commercial product. So we're going to take the pH, and we're also going to see how it reacts in the presence of vegetable oil. So we're going to put a couple drops of the vegetable oil in the test tube, shake it up, and see what happens. So take a picture of it before and after you've added the vegetable oil, because we want to see what happens to the vegetable oil. The next thing you're going to do is that there's a package. It's just called hard water mix. And basically all that is just magnesium and calcium salts. Now, what's the difference between magnesium, calcium, and the sodium? Because before, these have been in the presence of sodium. Then we're going to add magnesium and calcium. That causes what's called hard water. What happens with hard water? Has anybody ever had a hard water situation? What does that mean? Or has anyone ever heard of hard water or a water softener? No one's ever had hard water before? I grew up in a town where there was a whole bunch of iron. It was a steel making city, and there was a whole bunch of iron in the water. In fact, the water was horrible. It was actually kind of brown. It wasn't very good to drink. It wasn't much good for anything. It's been cleaned up a little now, but the water was really, really hard. Anyone know what that means? Yes, Megan, that's right. The soap won't foam. So you can take, it was awful for like taking a shower, because you'd be like, you'd have a bar of soap and you'd be rubbing it on yourself and it just wouldn't make any bubbles. And so it was really hard to get clean with hard water. And it also sucked a lot of the moisture out of your skin. So A, you wouldn't be able to clean yourself, and B, your skin would be all scaly and awful. So I don't recommend hard water to anybody. So, but what's the difference between the ions in the hard water and the ions that our soap is in now? After the soap you've made, what's the difference in the ions that the soap that you've made and the hard water ions? We have sodium down here. So that's the ion that's associated with our soap originally. And then in hard water, we've got these. What's the difference?
The charges.
The charges, right. So what's the difference between the sodium and the magnesium, calcium, and iron?
The sodium has a lower positive charge.
Right, this is just a single charge. These are all double positive. Plus twos. This sodium's just a +1. So in the presence of just the +1, this just neutralizes the single negative charge. And so you have a neutral, it's neutralized. And so it can interact with other neutral ions, and it's not a problem. However, in the presence of a double positive charge, then we form these weird complexes. Then you start pulling these head groups together in shapes that they weren't in before. Basically, you're forcing them into being associated with calcium, and you're forcing it into a specific shape. Whereas before, they were sort of just free to move around. And so once you do that, it makes it very hard to form these micelles, because basically it's sort of like sticking, the double bond in there. And you're sort of now, instead of it being sort of loose and easy and flopping around, now it's locked into position. And so you lose that fluidity. And so you don't get nearly as much micelle formation. And a lot of the times, the presence of these divalent cations will cause them to precipitate. And so they just fall out of solution entirely. So that's why hard water is such a problem. So you want to remove, calcium's good for you, and magnesium's good for you, and iron's good for you, but you don't want really high concentrations of it in your water, because then you can't wash your dishes or your clothes or your skin or anything like that. So what water softeners do is basically replaces these divalent cations with monovalent cations, mostly sodium. So if you go to the hardware store, you will notice these big bags of sodium chloride for water softeners, like these big 40-pound bags. So that's basically what they do, is try and get the divalent cations out and put the monovalent cations back in so you can make micelles again. Okay, any questions about what we're going to be doing tonight? Like I said, it's going to be pretty short. Since we're not going to have a lab next week, I figured we should have like an experiment that will take, we'll do a little bit tonight, and then you can finish it on your own next week. Any questions? All right, so 5 minutes, everyone gets their goggles and their gloves, and we'll get started, okay? All right, see you in a minute. All right, see Cassandra's gotten started. Okay. So we want 2 grams of our oil. There we go. Yeah. There we go. Oh man, you can see that they didn't put the cap on this quite tightly enough, and it's leaked out. There we go. 2.02 grams, close enough. Put the cap on a little tighter. Now you're going to need this again later, so the second part. So what I figured I would do is I'm going to do the experiment as well, and I'll just be sending out updates of what mine look like and see if you compare them to yours. So 2 grams appears to be about that much. So sodium hydroxide. So we just use our 10 mil cylinder for this one. I believe it was 2 mils. Is that what we want? 2 mils, wasn't it?
Yes.
Okay. Excuse me. Oh dear. Shouldn't inhale the sodium hydroxide. Then you want to cap this quite tightly. You do not want this coming back on us.
It said you need to shake it for 5 to 10 minutes.
No. We're going to let it sit for 5 to 10 minutes. So you can see it's already separated. Oil on the top and the sodium hydroxide on the bottom. You shake it for about 30 seconds or so. And then basically we will let it sit. And what we're hoping to do is to make an emulsion, just like everyone's made salad dressing before, right? Hopefully, with oil and vinegar.
Yeah.
Yeah, so you're basically just doing the same thing. Now, so a commercial company that would make salad dressing puts something called an emulsifier in their product. And all that does is basically keeps those small droplets from turning into larger ones. And the emulsifiers are basically sort of like a soap, except that they're edible. All right, so then, yeah, so you get something that should look like it's cloudy because basically you've had 2 clear liquids. And you can also see it's starting to separate it already. I'm just going to let that sit. basically we want that, just to separate, calm down, then we're going to shake it again. I'm going to give it like 2 more shakes. I don't think it's necessary. We can keep this in the dark. I don't think that's required. But even now, you can see that the top layer, before it was clear, and now it's cloudy. So it's basically, we're forming these micelles. They're pretty big right now. We want them to be as small as possible. I suspect what we want to look for is eventually, if we just keep shaking this long enough, the whole thing will look like the top layer. And then that will give us the maximum interaction of the oil with the hydroxide. Pretty interesting experiment, huh, Karina? More fun than watching paint dry. You got nobody in the kitchen with you tonight, Megan?
Oh, my dad's here.
Okay. You tell him you're making soap?
Yep, he's ready to use it when it's done.
Yeah, I don't think we're going to be making all that much, but
Hey, whatever helps.
yeah, the top layer is staying cloudy. So I think that's sort of what we want. It's like the whole thing to be cloudy. Yeah, unfortunately, the lab instructions didn't come with any pictures, so I don't really know. Since I haven't done this one before, I don't really know what to expect. I mean, I've made, salad dressing before. I sort of know what to expect there, but that's a weak acid, so you wouldn't really be making, it wouldn't be strong enough acid to break the bonds in the oils. So I've got a question for you. So we have these triglycerides, right? The triglycerides in the oil. When we do this reaction, we separate them into fatty acids and the glycerol. Where's the glycerol going to go? Is it going to be in the oil layer or in the water layer? Which do you think glycerol would be more soluble in, oil or water? If you remember what it looked like. No one wants to guess. What do you think? More? Yeah, water. It's much more soluble in water. It has 3 hydroxyl groups, all hydrogen bonding. And so it had hydrogen bonds like a Mo. So it will definitely go to the water layer. So when we filter it, we should be filtering all the glycerol away and just be left with the fatty acids. All right, I'm going to shake mine up again.
You don't need to wait 10 minutes?
I think it was 5 to 10, wasn't it?
It said allow the mixture to stand for 10 minutes, then shake it again.
Oh, I thought it was 5 to 10. Oops.
You're not reading the instructions like what you always tell us to do.
No, I did read the instructions. I was too old to remember them.
Oh.
There's a big difference. All right, I'll give it 10 this time. It does seem to separate awfully quickly. So you could see why in industrial soap making, why stirring, mixing would be so important. Because you can see these components do not want to mix with each other. So if you want that reaction to go, that's the other advantage of using high temperatures. The higher the temperature, the more soluble solids generally become. Most everything is usually more soluble in hot water than cold. With the exception of what? Anyone know what's less soluble in water as it gets hot? There's a whole group of substances that are less soluble in water when it's hot. What happens to a can of soda if you heat it up? Other than the can explodes. So Cassandra, why does it go boom, boom, kaboom when you heat it up?
Pressure,
Where's the pressure come from?
the heat,
Nope. Does come from pressure. What did we learn causes pressure? We learned this a couple chapters back. It's not liquid. We didn't really learn about liquids causing pressure, though obviously they do.
Gas.
Gases. Yeah, gases are less soluble in hot water. So that's why when you're making soda, for instance, the water has to be very, very cold for the carbon dioxide to dissolve in it. Because if it's too hot, the carbon dioxide would rather be a gas than be dissolved in water at high temperatures, and so it leaves the water. And that's where your pressure for your boom, boom, kaboom comes from.
I knew I was close.
Yep. I mean, yes, indirectly it is the heat, but it's the gas pressure. See if it looks any different from the first time. I can't tell if this is a little more. It's like maybe it's a little more viscous than it was before. A little bit.
Do you have to shake it until there's absolutely no layers? Because once I stop, the two layers begin to form.
Right. Yeah, yeah. I have to check. I mean, I can't remember. How long does it give you as a time to shake it? I mean, the best thing to do would be to put it on a paint shaker for 3 days, but not everybody can do that. Oh yeah, it does say to shake it for 5 to 10 minutes, doesn't it?
Yeah.
Sorry, I doubted you, Vera. Man, all right. Start the starter clocks. Yeah, just think of the forearm workout we're all going to get. It's going to make for a fascinating video.